Hello everyone. Today I'm reporting some joint work with my colleagues David Seifert and Serge Case. And throughout the talk, we're going to investigate the dynamical behavior of networks consisting of linear partial differential equations. And the motivation for this study is that dynamics defined on networks are inherently interesting. And this is especially pronounced in the case of networks of partial differential equations, because in this situation, both the network structure and the component dynamics of the PDEs contribute to the dynamical properties. And there are definitely several ways you could define something like a stability of a dynamical system or a network. And in this talk, we're especially focusing on the long time behavior of the solutions of the system and their energy. So we're mainly interested in what happens when time goes to infinity. And throughout the talk, I'm going to refer to a PDE network as a collection of individual partial differential equation models which communicate with each other in a way so that the communication and their interaction can be described by a graph. And this is of course maybe slightly elusive way to define the concept, so I'm going to begin by illustrating what I mean by concrete examples. So as the first example, we can consider these beam structures. For example, this bridge shown here, where we have a lot of physical metal beams that are joined together at their endpoints, so that they make up this kind of a structure that actually looks like a network. If we want to model this kind of a structure mathematically, then we would use, for each of these beams in this so-called truss structure, we would use a so-called beam equation, which is a partial differential equation, to model the deflection of the beam along the length of its length. In this situation, we could either consider the steady state properties of this kind of a structure, in which case we would use a steady state beam equation, but in order to study the dynamics of this model, of this kind of structure, we would use the time-dependent beam equation. And when you see this picture of a bridge, you wouldn't necessarily first think of dynamics, because these truss structures are usually built so that they have very rigid properties. But indeed, even in the case of bridges, the dynamics are really very important, because they can have a dramatic effect on the durability of the structure. So how we go from this kind of a physical beam model to this network of beams happens so that if we have a large scale or any scale beam network, a physical model like the truss bridge or the Eiffel Tower, then we can describe the connectivity of these individual beams with a graph where each of the beams defines an edge between two vertices, and the connection points of the endpoints of the beams are exactly the nodes or vertices of the graph. And I must say that there are also other ways you can think of PDEs on networks, but throughout the talk we just focus on this one situation where each PDE model is defined along an edge of the graph, and the connections between the PDE models are defined on exactly the nodes of the graph. And besides these beam structures, there are other examples of PDE networks. So one important example comes from like pipe networks, where we could, for example, consider pipes which are used to transport natural gas or water or fuel. And these can be, again, modeled with PDE networks, where each of the PDEs are defined to be this so-called transport equations describing the transport of mass with finite velocity. This doesn't need to be on the scale of whole Central Europe, but instead, for example, just a municipal water supply is a good example, and then also heat exchange processes might be modeled with using transport equations which are connected to get together. On the other hand, if we would be interested in modeling the water flow and dynamics in water channels like, let's say, central Amsterdam, the appropriate type of PDE for this would be the wave equation describing the dynamics of water waves. On the other hand, if we, in the case of, let's say, our metal bridge, we would be more interested in the temperature profile in the structure. We could use heat equation or convection diffusion equations to model the temperature diffusion in such a network structure. The next thing to consider is the way that the PDEs interact with each other over the network. And if we come back to our example of this beam structure like the bridge, we can take a look at what happens at the interconnections of these beams. And as we already mentioned, each of these beams is modeled by the so-called beam equation, which models the deflection over the length of the beam. So the actual differential equation is defined along the length of the beam, but each type of PDE also comes with a set of so-called boundary conditions which define the solution or some quantities related to the solution at the end points of each of these beams. And these boundary conditions are really important from a mathematical point of view to make the solution or the deflection profile unique. But these boundary conditions are also exactly how we can couple and connect these beams together at the vertices of our actual mathematical PDE network model. And in the case of beam equations, these types of boundary values that we can consider in these couplings are the actual deflections, maybe the slope of the deflection, and maybe the velocity of this beam at these endpoints. But this is a more general principle as well. So if we define PDE networks in the way we do in this presentation, then these couplings are really defined through boundary conditions of each of these PDEs. And we can look at a few examples. So in the case of our gas pipe network example, where the PDEs are transport equations, then the natural coupling in the network nodes would be the require that the incoming at each time the incoming mass flow is the same as the outgoing mass flow, and this is so-called Kirchhoff type condition, which is very natural for this mass flow. And in this case, this is definitely possible in the case to model with transport equations, where the natural boundary conditions, or the pretty much the only natural boundary conditions, are the mass density at the endpoints of the PDE. On the other hand, if we have a network of strings, or let's say very, very flexible beams that are connected to each other, we can model this situation with vibrating strings described by one-dimensional wave equations. And in the case where these strings are coupled or joined together at the edges, then the natural boundary conditions would be to require that the deflections of the beams that are joined together are equal at the connecting point, and in addition that the forces affecting these endpoint sum to zero. And in the case of our truss bridge, where we model this situation with beam equations, we could also have these conditions posed on the deflections being equal, the forces summing to zero. And in the case of beam equations, we would most likely also have additional similar types of conditions. So maybe the main point to take away from this slide is that for each type of PDE, there are these natural types of couplings that we can consider between the PDEs. And also the type of the PDE has an effect on the number of conditions we should pose at the nodes. And so already mentioned, we're interested in the study of dynamical properties and stability and long-time behavior of these networks. So let's make it a little bit more precise what we mean. And we, throughout the talk, roughly define stability to be the property that all the solutions of the PDE network converge to some steady state as time goes to infinity. And we're interested in the linear case, where we can always, just by a change of variables, guarantee that zero is in fact a unique steady state. And we can focus on this situation. And I'm going to interchangeably talk about stability and the convergence of energy of the solutions to zero as time goes to infinity, because in many practical situations these two things would be equivalent. But I'm going to describe things in a fairly general manner, but just to make a point about the terminology here. And now that we are studying the situation where the energy goes to zero, we're also very interested in the rate of this convergence. And so that's one of our focal points of our investigation, to estimate the rate of energy convergence as t goes to infinity. And one of the other key points in this talk is that we're specifically interested in studying stability of networks that involve two different types of PDE models in them. So instead of just having a simple beam structure, we we're considering situations where we have instead of only beams, also something else. So from a, let's say, an example point of view, we could think about this like a suspension bridge where we have this kind of a beam truss structure as before, but in addition we have these cables which may vibrate and cause some additional dynamics in the system. And one of the key examples that I'm going to use to illustrate the results comes from interconnecting wave and heat equations on the network. And combinations of wave and heat equations are especially used in modeling so-called fluid structure interactions in flow problems. Alternatively, we could have the same type of PDE, let's say the wave equation, but with two different types of dynamical properties. So we could have a network where we have wave equations with damping and wave equations without damping, or alternatively beams. So with these points, we focus on our investigation into the stability properties of these networks, which involve two different types of PDEs. And one of the key motivations is that this mixture of different PDE types makes the network dynamics specifically interesting. And one of the points from the stability theory point of view is that it's observed in the literature that often when you combine two different types of PDEs, then you may run into stability properties where the convergence of the energy is slower than exponential, and this leads to but instead it's usually a rational rate, and this leads to so-called polynomial stability of the network. And in this, especially in this situation where we know that we have a sub-exponential convergence rate of the energy, it's a very interesting question to derive accurate and optional. And in this situation where we have a sub-exponential decay rate for the energy, it's an interesting question to attempt to derive as accurate as possible and preferably optimal decay rates for the energy. Okay, so let's get into our actual main results in the stability analysis. And I'm going to illustrate these results and talk about the general approach first by considering this example network consisting of some wave equations on the blue edges and heat equations on the red edges. In our stability analysis, we use a spatial approach where we begin by splitting our network into two parts. One consisting only of those edges with the wave equations, and then the other just consisting of the heat equations. And then we take a system theoretic viewpoint where we consider these two parts of the network to be separate dynamical systems which exchange information at these selected nodes. And in systems theory, this kind of a configuration is known as a feedback structure, where we have indeed two separate dynamical systems, each equipped with some dedicated input signals and output signals, and they interact or are coupled together in this kind of a feedback configuration where the output of system 1 is fed into the input of system 2 and vice versa. And this is indeed a well-known and very, very useful concept in systems theory. And in addition, we identify from our network a situation that one of our systems, namely the wave network, consists of dynamics that are inherently unstable and very oscillatory. On the other hand, the heat network consists of diffusive dynamics, which are on the other hand very stable type of dynamics. And indeed, this full interconnection then makes up our full wave heat network. And motivated by this, we're interested in what kind of properties of system 1 and system 2 would guarantee the stability of this full system when we put these systems together. And the way we can investigate this is that we can, for the moment, break apart this interchange of information or this feedback structure between the two parts of the network. And instead, we can take a look at what the dynamical properties of these two systems are when we also allow them to have these inputs and outputs. And there are a lot of benefits for thinking about this stability of this wave heat network in terms of these component systems. One of them is this fact that by splitting these into two parts, we're reducing our analysis to some relatively simple components of the full network. And because of this, the kinds of conditions we need to pose on these two systems are relatively easier and simpler to check and verify than what kind of conditions we would need for the full coupled system. The other benefit is that when we split this into two parts, we, for example, reduce our example network to the study of this wave network and a heat network. And it's possible that when we pose some conditions on just the wave part, we can already find this kind of information we need directly from the literature, because there are several investigations on just the wave networks consisting of wave equations. Or similarly, the heat equation networks are better understood and more actively studied in the literature compared to wave heat networks. And finally, we have the benefit of modularity as well. So for instance, if we carry out our analysis for the wave heat network by splitting these things into parts, then if we, as our next topic, would like to consider instead the dynamics of a beam heat network, then it's possible that we only need to replace the analysis parts related to this wave part of the network, and maybe we can use directly our earlier results and properties that we proved for our heat network. So now that we have our agenda, we can go into our main results. And this starts with listing the kinds of assumptions we need on our systems. So the two systems we consider are assumed to be so-called impedance passive. And I don't intend to go into detail about this. This is a system theoretic concept, but it's something that is relatively easily checkable in the setting that we work in. And this is something that could be described as the property that neither of these systems has any internal sources of energy. So let's say the heat part shouldn't have any reactive terms. This is a special class of systems, and it does definitely narrow down the kinds of models we can analyze. But at the same time, this is a very like a common property of many mechanical systems and these types of. It's a very natural assumption, let's say. And then we can go into the assumptions on the individual component systems. So we first take a look at the unstable system 1. And for this system, we assume that if we take the output y1 and then insert it into the input of the same system, but with a negative sign, then we get a stable system. And this is known as negative output feedback in systems theory, but in the context of these, let's say, wave networks or similar types of network PDEs, this interconnection of feeding the output of the system with a negative sign to its input very often corresponds exactly to adding some damping to our system. So in fact, this way, the assumption that the system 1 becomes stable under this interconnection is very natural, because it means that adding some damping to the system should stabilize it. And finally, we should pose an assumption on the stable system 2. And in the case of this system, we assume that we know the way, something very specific about the way that the system turns inputs into outputs. And more precisely, we assume that we know how this system maps the Laplace transform of its inputs to the Laplace transform of its outputs. And this map has, again, a very, very concrete meaning in systems theory, and it's called the transfer function of the system. So this is indeed a systems theory concept, but maybe here the most important thing to emphasize is that in cases of many PDE networks, this is something that can be explicitly computed, or it may be already known from the literature, or alternatively it can be reliably estimated. And so if we have all of these assumptions, we can now state our main result. So more specifically, we assume again that the two systems are impedance passive, and we assume that our system 1, with this addition of the damping, becomes stable, and we know some estimate about its energy decay rate. And finally, for the system 2, we indeed assume that we know some estimates for the transfer function of the system on the imaginary axis. And if all of these conditions hold, then our main result is that we can in fact prove that when our full wave heat network is indeed stable, and we also have a very good estimate on the decay rate for the energy of this system. So I'm still using the wave heat network to illustrate these results, but in fact this theorem that I'm showing you here applies to quite a large class of different types of PDE networks of mixed types. And before going into the illustration, I have one fairly technical slide which is just describing the mathematics behind this result. And I won't go into much detail here, but I want to say a few words about really the techniques. But like I said, this is the only slide here. The framework that we work in the abstract setting is like infinite dimensional evolution equations, where we consider two dynamical infinite dimensional differential equations which are coupled via these two algebraic conditions. And these kinds of coupled systems have been studied before in the literature, and it's, for example, been shown that this full system here is associated with a contraction semigroup. And in the main results, we analyze the dynamics of this system by investigating the spectral properties of the associated generator and by establishing a very good resolvent estimate for the generator A of the semigroup of this system. And this resolvent estimate especially has the feature that consists of two separate parts. One associated to the properties of this system, system 1, and then the other one related to the second system, for example, the heat part of the network. And with this resolvent estimate and the knowledge that we have a contraction semigroup, we immediately get results on decay rates for energy of the system, because we get either polynomial or so-called semi-uniform stability of our semigroup. But this was the technical part, so let's get back to the or applying our main theorem for analysis of some concrete networks. So in this example, I'm interested in the dynamics of this kind of a network consisting of n wave equations and a single heat equation coupled to some exterior edge of the wave parts. And in order to apply our results, we split this heat equation apart from the wave part with the suitable boundary conditions and boundary coupling. This fits our framework of impedance passive coupled systems, so we can apply our results. When we apply this so-called negative output feedback to our wave network, this indeed exactly corresponds to the damping at this single exterior node. And this is a good situation for us, but because especially exactly these kinds of systems have been studied, and wave networks have been studied in the literature before, so we can use some existing results. On the other hand, in the case on the side of the heat equation, this is something that's really well understood from the PDE systems theory literature point of view. And in this case, the transfer function can actually be explicitly computed and we get very good estimates for it. And one of our first main results that we can pose is that we can make some assumption on the energy decay in this wave part of the system. So if we have that this damping creates some rational decay rate for just the solutions of the wave part, the classical solutions, then our results applied to the system show that we also get a rational decay rate for energy decay rate for all classical solutions of the coupled wave heat system, but with a slower but a very specific rational decay rate. We can also look at specific situations, and for example, using the results by Julie Valain and Enrique Suazua, we can get some concrete, even more concrete estimates. So in this situation, we assume that our network is like pictured here, so it's star-shaped, And if the waves have same speeds and then the ratios of the lengths of the wave equations are irrational numbers satisfying some additional properties, then we get our results give a very specific rate for the energy decay of classical solutions of our coupled network. I haven't commented on the existing literature yet, but I should mention that many of the topics we've talked about today have also been investigated by many authors in the literature. Especially PDE networks have been studied a lot by people like Enric Suasua, Kai Samari, who have contributed a lot to this area. A lot of the investigations involve single type PDEs, but also different dynamical aspects and for example, dynamic couplings have been investigated. Also, the area of coupled PDEs of mixed types is a very active field of study, especially from the point of view of these couplings modeling fluid structure interactions, where you have coupled parabolic hyperbolic systems of PDEs, and especially the school of involving George Avalos, Irene Lassi, and Roberto Tricciani have contributed a lot to this area. Also, some network studies involving several two kinds of PDEs have been studied in the literature. Also, since we work on the setting of abstract systems, I should mention that there are also several existing studies on stability properties and dynamical features of coupled systems, of coupled abstract systems. And this brings me to the end of my talk, where I've investigated the stability properties of networks consisting of PDEs of different types. And as my main result, I've shown you a description of a new mathematical result written in the context of abstract coupled systems, which will hopefully be a very useful tool in analyzing networks consisting of partial differential equations. And this result is contained in this first article shown here, which is published on arXiv. So thank you very much for listening.